Hello everyone, and welcome back to Don't Be a Fossil Fool channel. This week we'll be discussing the first law of thermodynamics, how it works, and how it relates to climate change. But before you turn this video off or let out a sigh of exasperation, our goal as always is to explain these physics terms as simply as possible to non-experts who just want to learn a little bit more about climate dynamics and variability. Meanwhile, the physics experts among you can feel free to stay for the terrible puns. And believe me, this is actually interesting, unlike friction, which is a total drag. Okay, so the first law of thermodynamics is commonly referred to as the law of conservation of energy, which states that energy can neither be created or destroyed, but can only be converted from one form to another. So let's start with a little background. When examining its humble beginnings, you'd find that the first law of thermodynamics was predated by the caloric theory in the late 18th and 19th centuries, which treated heat like a fluid that flowed naturally from hot to cold regions, just like water flows from high to low places. When this fluid flowed from hot to cold, it could be converted to kinetic energy. This could then be made to do work, just like you can see when water flows over a water wheel, making it move. It wasn't until German physicist Rudolf Clausius, godfather of thermodynamics, published the mechanical theory of heat in 1867, which subsequently burned the caloric theory. Get it? Burning calories? Anyways. As if that wasn't enough, later in the 18th century, Benjamin Thompson, also known as Count Rumford, asserted that heat was not like a fluid. While he was boring a cannon, basically making the hole for the cannonball to shoot out of, he realized there seemed to be limitless amounts of heat as the drilling continued, though he was unable to adequately express this relationship as atoms and molecules weren't common knowledge yet. Then came along James Joule, the namesake of the measurement of energy. He performed quantitative measurements to compare mechanical work and heat, raising the temperature of a known quantity of water by the same amount. Thus, the basis for the first law of thermodynamics was formed. But to really make sure you understand this, we should define a couple of things. There are two essential components in thermodynamics, the system and the surroundings. The system is simply the region of the universe under study, while the surroundings include everything else in the universe that's not in the system. This is important because everything that exists is some form of energy. There are atoms and molecules that old Count Rumford wasn't quite seeing. Whatever this energy is, we cannot create or destroy it. It only changes to different forms. But if we take the sum of all forms of energy, it cannot change. Sound familiar? So, our first law is expressed in its differential form as du is equal to dq minus dw. du refers to the change in an internal energy of the system, like a parcel of air, while dq refers to the heat added to the system, and dw refers to the work done by or on the system. In essence, we're defining internal energy as equal to the difference in heat transfer into a system and work done by a system. These figures are typically expressed in units such as joules, but sometimes they can be expressed as newtons or force. Some classic examples of these can be seen in adiabatic processes, in which no heat is added or subtracted, just work being done on the system. Less dense parcels of air start to rise due to buoyancy. However, another common example is a heat engine. This is easiest to show visually with a steam engine. With the piston moving up and down, hot, high-pressure steam is admitted into a cylinder, then allowed to escape. This process is work being done. Heat is generated by burning a fuel to make steam, convert part of it to do work, and exhaust the remaining heat to the environment at a lower temperature. The net heat energy is absorbed, and since the engine returns to its initial state, its internal energy doesn't change. This system relies on the overall conservation of energy. Because of the first law of thermodynamics, we know that no energy is created or destroyed in this system, only transferred between each part. In order to save money on fuel and avoid contaminating the environment with waste heat, nowadays engines are designed to maximize the conversion of absorbed heat into useful work and minimize waste heat. There you have it, a quick and easy way to understand the first law of thermodynamics. Really takes the pressure off, doesn't it? Now that you understand the gravity of the situation, it's time to go. Thanks for watching!